Today we're going to talk about a new AI system based on reinforcement learning that is called Alpha Tensor, developed by DeepMind. And it was created to discover novel and more efficient algorithms for performing matrix multiplications. And probably I don't even need to clarify how huge the influence of matrix multiplications is in every kind of computations. So even the tiniest improvement of this procedure may be really significant. So during this paper review, we are going to firstly talk about matrix multiplication algorithms. Then we will take a really quick look at some primary basics of the reinforcement learning framework. And finally, we will discover how Alpha Tensor is constructed and how it is actually learned. And at the very end, we will consider some quantity specifications and even some side-away purposes for which the Alpha Tensor has also shown promises. And for the beginning of the review, we need to know that the problem of discovering a matrix multiplication algorithm is formulated as a single-player game called Tensor Game. And to solve this game, the authors developed a deep reinforcement learning agent called Alpha Tensor that is built upon AlphaZero, known as an agent for that is with a superhuman performance on board games like chess and Go. So considering matrix multiplications, we usually remember this standard row column way. And in fact, that was the only discovered way until mathematician Folkesthassen derived a 7 steps algorithm instead of standard 8 steps for 2x2 matrix multiplications. And this innovation, it led to some additional consequences. That firstly, the computational cost of matrix multiplications may be reduced since the multiplication operation is much more expensive operation compared to addition. And the second is, are there any strategies for multiplying matrices of higher dimensions? But it found out that discovering a more efficient algorithm, even for 3x3 matrices, is complicated enough for a human's brain. In fact, any matrix multiplication can be presented in the form of a binary 3D tensor, where its dimensions correspond to values of each matrix. And this tensor specifies which entries from the input to read, from the input matrices, yes, and where to write the result. For example, let's consider the C1. We see 2 entries along the C1 dimensions, here and here. And the first entry stands in the intersection of B1 and A1. That means that corresponding scalars are multiplied. The second is the intersection of B3 and A2. And as a result, C1 represents as a sum of all entries, where each entry is a multiplication. And if we continue considering exactly this tensor, we will end up with a usual 8-step row column algorithm. And well, this 3D tensor, that is what represents a tensor game I mentioned before, which the agent has to solve in the best way. And the solution of the tensor is is done by solving the decomposition problem. So by tensor decomposition, we mean decomposing a tensor into individual components via the sum of the outer product of vectors. And the intuition here is that each outer product triplet represents a single multiplication step in the algorithm. Exactly here, we consider a Strassens algorithm as an example. You may follow these green, purple, and orange colors in order to somehow link the equations with decompositions, or we can consider the construction of C1 that I painted. So it is a sum of series entries, and any entry, for example, let's consider M1, is a single multiplications of U and V vectors. And if you continue combining the whole decomposition, you will end up with this beautiful tensor that shows us how the Strassens algorithm actually looks like in kind of geometry. Thus, in order to solve this tensor game, the agent has to choose all these vectors whose composition has to converge with the target tensor. And the tensor game is solved with reinforcement learning. And today's meeting is not about reinforcement learning, but I have to mention some very primary basics of it, since it won't be possible to understand the alpha tensor without it. So you probably heard that reinforcement learning is a framework for training an agent to make a sequence of decisions in some sort of environment to maximize a reward. And a typical reinforcement learning model can be represented with this flow, where a computer is an agent and it observes a state of the environment. And it takes actions based on the state to the environment. As a result of the performed action, it receives feedback as a reward or a punishment, and it also gets a new state from the environment. And the agent has a goal in this flow is to achieve a maximum reward. And here come two important functions, policy and value. So the policy function, it estimates the probability of whether an action is in the given state is more likely to lead the reward. And the value function estimates the value of being in a certain state with a given policy. So agent always decides on policy, and policy is designed by value. And there is a hard optimization problem, and there are lots of strategies, explanation of which go much far beyond this paper review. So today we are aiming at exactly the alpha tensor model. Now we can dive into the alpha tensor neural network. It is transformer based, and it contains of torso, policy, and value head. And as input, it takes a current state and the history of states. These states are fed to neural network in order to choose more likely action. And the action space here is to select three vectors, U, V, W, such that at first time step, the network predicts first column of UVV, UVW. At the second step, it predicts second column, and so on. Let's briefly look into each part. Here is the torso, and it is something similar to a feature encoder. It takes states and it encodes them into some sort of embedding. And the intuition here is to reduce time dimension with linear mapping and applying attentive models. Here is how the policy and value head look like. And I don't really want to go into details here, especially for the policy. So in simple words, the policy takes an embedding state and tries to predict the distribution over the action space. And the value head is a simple MLP which processes the embedding from the policy into the value of how the current state is likely to be in the direction of reward. And here is a tiny figure explaining optimization procedure that is done with Monte Carlo research. It helps neural network to consider several pathways and pick the best one and learn from this whole procedure. So in this tree, at each stage, you just like ask which path should I consider based on the policy, and whether should I stop considering this way based on the value. So the pathways are something like weighted with policies, and the nodes here like the value of a state. Finally, we can take a look at the whole framework. It is divided into two sections, acting and learning. Acting is about playing the game. So for input comes a binary 3D tensor, which decomposition the agent has to solve. And at each step, the game of this game, the agent selects this UVW triplet and updates the state by subtracting the sum of the triplet. And the goal here is to reach a zero with the lowest number of moves. When the game is played, here comes the learning. And they randomly combine played games with some synthetic demonstrations. They feed it all to the neural network, which learns the policy and the value head. And here are some notes on that, important notes. So in order to teach the agent to perform decomposition with the lowest number of multiplications, it receives a -1 reward at each step. And in the case of losing this game, it also receives a negative reward. So finally, we can explore some quantitative specifications. So on the left figure is a comparison of matrix multiplication complexity measured by the number of multiplications. And we see that alpha tensor either rediscovers, yes, or algorithms, or it derives a novel one that are more efficient. And on the plot here is the tendency of improvements depending on the rank of the matrix. So alpha tensor has more significant improvements for matrices with higher ranks. And here I want to introduce to you one of the algorithms discovered by alpha tensor, which is for multiplying 4 by 5 with 5 by 5 matrices. And it takes 76 steps instead of usual 80. And the whole procedure on the slide, humanity hasn't ever seen or derived before. All these steps were discovered by the alpha tensor, and that is really incredible, I think. Another amazing use case of the alpha tensor is applying it for finding efficient matrix multiplication algorithms tailored to a specific hardware. For that purpose, the algorithm had just modified they just modified the reward of the alpha tensor by providing an additional reward at the terminal state of win, only for win, that is equal to the negative of the runtime of the algorithm, which is benchmarked on the target hardware. And they studied two hardware devices whose comparison is on these plots. And you see that algorithms discovered by alpha tensor are much faster than usual ones. And the last plot shows the importance of tailoring discovered algorithm to the particular hardware. As algorithms optimized for one hardware do not perform as well on other hardware. That is probably obvious. Yes, conclusions. In conclusion, the alpha tensor, yes, we know it discovers matrix multiplication algorithms that are more efficient than existing algorithms are. And in particular, novel algorithms from alpha tensor will speed up lots of computational tasks. But in general, I guess this paper is a huge inspiration for leveraging the idea of training an AI to solve other fundamental computational tasks which humans haven't solved before. And at the very end, this research really impressed me, I guess even more than recently trending language models do, because it's not only about matrix multiplications, but it also about going beyond the human intuition. So thank you for your attention. I hope you enjoyed it, decided.